2.5. Example 7. It says the graph above shows the position y of t of a particle in inches. Now, if the position equation is y of t, the particle will probably be moving what? Horizontally or vertically? Maybe vertically, hopefully. Not necessarily. You could define the position to be any variable you want. But in this one, we're moving along a vertical line. So in the previous one, we were moving up and down, or left and right. Now we're moving up and down. So you can kind of use the vertical axis of the coordinate plane, to imagine that this particle is just going in a straight line, either up or down. And notice that we have another specified interval here. This is only good from 0 to 7. 0 to 7. We do have units. That's important. We got inches and we got seconds. So every numeric answer should have units on them. All right, if you want to just look at the graph and familiarize yourself, this is y of t. So the y values of this graph will tell us where the particle is on the y-axis, yes, at any given time. This is not the graph of the particle's movement. He's not following along this crazy-looking hill or anything. The slopes of this graph will represent what? The velocities. The slopes are the velocities. That's important to understand. So that's how you need to calibrate yourself for the graph. The y values are the positions, and the slopes are the velocities. Okay. On what open intervals is the particle moving down? It says to justify. You can justify before you answer the question, or you can justify after you answer the question. It doesn't matter. Sometimes, though, justifying before you answer the question helps you answer the question. So let's do that one. A particle is moving down when the what is what? I'll get back to it. A particle is moving down when the what is what? Particle is moving down when its position is decreasing, right? Which that would mean its velocity is negative. So let's go ahead and say that. That's when v of t is less than 0. Now, we have to be careful here. I just said v of t is less than 0 because I'm pulling that out of memory. The velocity is negative. Did they give me the function v of t anywhere here? No. What you want to do is relate it to what you're given. You're given y of t, and v of t then is the what in relation to the graph of y? First derivative, which represents the what on the graph? Slope. So that's when the slopes of y of t are negative. Okay? This is kind of the critical justification. You could say y prime of t equals v of t, which is less than 0. But by saying y prime of t, you're not again hitting the nail exactly on the head, because you're not specifically saying that y prime are the slopes of the graph. It wouldn't be wrong to do that, but I would encourage you to relate it specifically to what you're given. So we're looking at the slopes of y of t, and we want to know where the slopes are negative. Okay? So now you could just say this happens or occurs, whatever you want to say, on, and then we look for the interval. Where are the slopes of the graph negative? Well, from where to where? 2 to 4, right? From 2 to 4 and 6 to 7. Open intervals or closed intervals? Yeah, it says open intervals, so we're not going to fight over the endpoints. So the slopes are negative on, what do we say? 2 to 4 and 6 to 7. So on 2 to 4 union 6 to 7. And does that have any units on it? Seconds, good. So then you can just add it at the back end of that in seconds. So notice then the justification came first, and it gave us something to look for then on the graph, and then we just answered the question. You could have said the particle is moving down on these intervals since on those intervals the slopes of y of t are less than 0. That would be answering and then justifying. All right, the next one. On what open intervals is the particle at rest? Well, the particle is at rest when what? Right, when the velocity is 0, so that's when the slopes of y of t are equal to 0. This occurs instead of happens. That works well. This occurs on. Okay, well, let's come back up here to the graph. Where is it? 0 to 2, right? 0 to 2, that's the only horizontal piece, so 0 to 2. This occurs on 0 to 2 seconds. Now, if you don't want to say on that interval, there's another way to do it. You could say for 0 less than, it's open interval, so 0 less than t less than 2 seconds. You could do it like that as well. Interval notation is pretty nice. So again, we justified already. The justification was this piece right here. Slopes of y of t are equal to 0. Again, that relates specifically to the graph of what they gave you. At what times on the open interval does the particle change direction? Justify. Okay, so what are we looking for? Is it where the velocity is 0? It's not where the velocity is 0. It's where the velocity changes what? Signs. And the velocity is the what of this graph? The slopes, right? So it's where the slopes of this graph change signs. Yes? Okay, so let's go ahead and say that. It is where the velocity changes signs, but this is going to be where the slopes of y of t change signs. Now remember, you have to say how they change, unfortunately. It doesn't really matter for a direction change, but we do have to say how they change. So we might have to actually spice up our justification. What's the first t value where the slopes of this graph change? Change signs. Did I say change signs? Yeah, change signs. 4. There are negative slopes to the left, positive slopes to the right. And where's another one? Do we have another one? At 6, the slopes change from positive to negative. Now, because they change 2 different ways, unfortunately, we have to say 2 different sentences. I'm going to write that right here where I can see it, and then maybe I'll bring it down. So, the particle changes direction, or directions, first of all, at t equals 4 seconds with units, since the slopes of y of t change from positive to negative. Where? At France? In France? Nope. They also change at t equals 4 seconds. So you'll get used to this type of notation. You're saying where it happens, and then the justification is saying it because that's also the place where the slopes change from positive to negative. Yeah, oh yeah, I was looking at the next one. Sorry, that would be wrong. That would be unfortunate. At 4, they change from negative to positive. Good. Yes, direction or direction. I said directions because I knew I was going to do it twice. You could say it changes direction at, and then at. That's fine. Directions. Well, yeah. I don't think you'd lose a point for that. If it's changing direction twice, is that plural? It's more than one direction change? I don't know. Hopefully there's no more than one direction change or my daughter's going to be crushed because she's still not over what's-his-face leaving. But if they did break up, right? They're kind of broken up for a year, one direction. They're going to do their solo things, which, yeah, they've got multiple directions. There you go. Do you think they'll ever get back together? I don't know. As long as Harry puts out a solo album, I think my household will be safe. I don't know when it happened. I don't really keep up. Apparently, the smoker left the band. Smoker? There was a smoker in the band? Yeah, he smoked. That's all. That's what I know him, the smoker. Okay. At 6. So it also changes at t equals 6 seconds since, see if I can get this one on my own, guys, since the slopes of y of t change from, don't tell me, positive to negative, not in France, but at t equals 6 seconds. Yeah. I can't even think of the guy that last name. It's Liam, and then there's and then there's Harry, and then there's One Direction, right? Yeah, One Direction, and then there's Niall, Niles, I don't know, Neil, and then there's 2 more. I don't know. Gosh, I can see their faces. They're all over my daughter's bedroom, but their names, who knows? Okay. So that's what we would answer right there on part C. So if you want to shrink that down and put it there in part C, we'll cut it. Oh, that didn't work. Come on, technology. Cut. And paste. Louis is one of them. They're coming to me now. Louis. Help me someone with the next one, please. Help me. The guy that left, the smoker. Zane. There you go, Zane. Good. Way to go, Miller. All right. During the first 6 seconds, Nick, changes from positive to Nick. Nick knows who Zane is. During the first 6 seconds, what's the particle's displacement? How do we find displacement? Displacement is the net change in position. So we'll write it out. Displacement is going to equal final position minus initial position, right? So the final position at the end of the 6 seconds is y of 6 minus the initial position is y of 0. So go ahead and write that out. Now, how are we going to get those values? From the graph. Yeah, very good. Y of 6 is 0, and y of 0 is 6. How about that? So y of 6 is 0, and y of 0 is 6. So that's negative 6. And what are the units there? Well, it's displacement. We're talking about y value, so it's feet. And explain what this means in terms of the particle's position. Inches, not feet. Dang it.
I mean, you could change it.
No, I don't want to convert that. No. This is where you kind of get tunnel vision when you're working on the iPad with all the pinch zoom. All right, let's go ahead and write the sentence. Who wants to try the sentence? Start with that introductory adverbial clause. You can use their terminology if you want. During the first 6 seconds, comma. During the first 6 seconds, comma, the particle. Could you use the word is displaced or the words is displaced? Would that work? That would work, right? Is displaced or ends up, however you want to say it. Now, you do want to interpret the sign. So, displaced 6 inches, yeah, below, right? So, it's displaced 6 inches below its starting position. Or it ended up 6 inches below its starting position. Does that mean it was moving down the entire time necessarily? Not necessarily. Was it moving down the whole time from 0 to 6? No. We know that it changed directions at 4. That's how we got started on that whole band discussion. That was probably my fault, right? All right. During the first 6 seconds, through how many inches does the particle travel? Is that the same as displacement? No. The total distance traveled is the total gross distance, not the net change in position. So if you're looking up here, does it travel anywhere from 0 to 2? No, because the slope is its velocity is 0. So it stays at y equals 6 on the number line for the first 2 seconds. Okay, now I know that it moves down from what to what? From 6 to negative 6, which is how many units? 12. So let's go ahead and show that. How would we show that? I would just say it's the absolute value of 6 minus negative 6. If you find the distance between two numbers, you subtract them. I'm just going to take the absolute value to make sure it's positive. So you can do negative 6 minus 6 or 6 minus negative 6. Subtract them. And then we're looking just on the first 6 seconds, so we got to be careful here. Here's 6. Now we're looking from here to here. Then in the next 2 seconds from 4 to 6, it moves back up. How many units? It goes back up 6, so I'm going to go ahead and say then it's 0 minus negative 6 plus, we'll add those together. And now we essentially get 12 plus 6, which is 18 inches. Now, for something like this, you probably wouldn't have to show this step here, simply because from the graph you can kind of count. It is nice to show this step, though, 12 plus 6, because what 12 plus 6 does is it kind of numerically indicates your method. It numerically indicates your method. And on a free response, in general, it's a bad idea to kind of just have something appear out of nowhere. But if you go 12 plus 6, you know, that's basically breaking it up into the two different movements, moving down and moving up, and adding them together. Two different what? Oh, like two different words for traveled?
No, there's two different words. There's one with one L and one with two L.
Okay, did I use the correct one?
The correct one, but that one, the one you just wrote, is the adjective for something that's traveled.
Oh, like he is well traveled. He is a well-traveled traveler because he has traveled many miles. Interesting. You know, I didn't really know that. Now anyone who watches this video will know that. Yeah, that was Wes, not Miller. Miller's the guy that you go to for the One Direction trivia, and Colton's the guy who knows the grammar and words. Yeah, okay. So the particle traveled 18 inches just to net 6 inches below its starting position. What is the particle's velocity at t equals 5? The particle's velocity at t equals 5. Explain what this means in terms of the particle's movement, okay? That's the instantaneous velocity, isn't it? So that's going to be the what of the graph at 5? The derivative. Now from the graph, that's the what? Slope, right? How are we going to find the slope at that point? My goodness. I can use the 2 points, right? I can find the slope of that line. So this is the ordered pair, not in highlighter. That's the ordered pair 4, -6. And this is the point 6, 0. So down below what I would do is I would say, here's where you can use the notation. You could say y prime of 5 equals v of 5. And I can say y prime there because what I'm about to do is I'm about to use the difference quotient. And I'm going to show that. So 0 minus -6, that's the change in the two y values, over 6 minus 4. And that gives me 6 over 2, which would be 3. That's the slope of the line. And what would be the units there? Inches per second, because that's units of the numerator over units of the denominator. So now that I have that written there, let me go ahead and cut that. Again, this is the iPad getting tunnel vision. It's nice when you have everything kind of out in front of you and you can just move your eyeballs instead of sliding up and down. Okay, so what's important to show right there? Well, at least y prime of 5 and the difference quotient, because now that implies that you're finding the slope. And then, of course, the answer with units. Everything else is kind of nice to have. What does that mean in terms of the particle's movement? So, again, here we'll say at t equals 5 seconds. We start with that introductory adverbial clause representing the moment in time with units. The particle, now you could say the particle's position is increasing, but that's kind of vague. Particle's position is increasing, yes, but that means that the particle's moving up or down. Which one? The particle is moving up. So the particle, let's not use a contraction there so we don't get confused with possession. Let's just say the particle is moving up or upward. Is there a difference, Mr. West?
Is it upward or upwards?
Oh, let's just say up. How about that? It's moving up at 3 inches per second. I would say it's moving upwards. No, I would say upward. I would say upward. Yeah. Because upwards is kind of like when you get older. It's like it's that thing. The price went up. It's upwards in the vicinity of like too much for me.
So really, when you get older,
You just kind of start misspeaking. Right? Yeah. I don't know. It's a good question. Upwards. I don't think you're ever going to lose points on the calculus test for little things like that. Okay? Maybe so. Maybe we should, right? At t equals 5 seconds, the particle is moving up at 3 inches per second. There we go. What is the particle's velocity at t equals 5.99999 seconds? Ooh. Why would it be just 3 inches per second again, Mr. Rapp? Right. We're still on that line segment, right? We're still on that line segment. We're still on the open interval that the line segment contains. So yes. Now here's what we say again. V. Let's do it again. Let's do y prime of 5.9999 equals v of 5.9999, which equals 3 feet per second. Did it say to justify? Bless you. Inches. God, why am I going with feet? I don't know. It does not say to justify. So in this case, you could just leave it like that. As long as it's tied to the right notation, you could just leave it like that. And that's one that they would expect you to know is the same as the previous, so you wouldn't have to set up the difference quotient all over again and reinvent the wheel. Now, what's the velocity at t equals 6 seconds? 0? Well, the derivative is the velocity, right? And the derivative are the slopes of this graph, right? So what's the slope of the graph at 6? It doesn't exist. Why not? It's not differentiable. You got a sharp turn. You got a sharp turn. So this thing actually changes directions there, we already said, right? Because the velocity, which are the slopes, go from positive to negative. So at t equals 6, this particle goes from moving up to down. The question is, how does it change directions? Does it change directions in a way that we can physically accomplish ourselves? No, because in one instant it's going up, in the immediate next instant it's going down. And I can't really think of anything in the real world that could change like that, except maybe we said some of the subatomic particles maybe in an accelerator. I don't know if they atom smash, if something hits something that's traveling the speed of light and it hits an immovable force and it bounces and recoils the other direction. Is that instantaneous change? I don't know. But the answer to this question is certainly what? dne. So we'll say y prime of 6 equals dne. Did it ask us to justify? No. If it did, you wouldn't just say since there's a sharp turn there. Remember, it's not differentiable because the slope from the left doesn't equal the slope from the right. It's a good thing it didn't ask us for that. They wouldn't ask you to justify that here. All right, during what open time intervals from 0 to 7 is the particle's speed the greatest? Speed. We haven't talked about that. We said that the slopes are velocities. What are the speeds? The absolute value of velocities. So it's the absolute value of the slopes. So the speed, the greatest speed, let's go ahead and write that down here. The greatest speed on this graph is going to be where the graph is the steepest, right? Now it could be the steepest in any direction with a positive or a negative slope. So we can kind of just calculate that very quickly. What's the slope from 6 to 7? Is it as steep or steeper than it is from 0 to 4? Here we go down 3 and right 1. So the slope here is negative 3, right? The slope here we said was positive 3 going up. So those would have the same speed, right? Okay. The speed between 0 and 2 is 0. What's the speed here? I know the velocity is the slope. Did we calculate the slope of this line? We go down 12 and over 2. Down 12 and over 2 is the slope of negative 6. So the velocity is negative 6. But the speed is what? Positive 6. Is 6 greater than 3 and 3? Yeah. Individually 3 and 3. If you put them together, then they're equal. But that's not what we meant, right? So, we'll just say then the speed is the greatest on the open interval from, what was it, 2 to 4? 2 to 4. And we'll put seconds behind it. Did it ask us to justify, or did it give what the speed was? No. On what interval or intervals is the velocity the greatest? Is it the same? Because velocity is a vector. The sign matters. So now we've got a positive 3, we've got a negative 3, and we've got a negative 6 for our velocities. Which one of those numbers is the greatest? Positive 3. And that's going to occur on the interval from 4 to 6. So that's the difference with velocity. The greatest velocity is where it's the most positive number or the least negative if they're all negative. Velocity is the greatest on the interval from 4 to 6. And it didn't ask us to explain what it was, what the actual number was, or why. All right, what's the particle's acceleration at t equals 3? Particle's acceleration at t equals 3. Okay, well, let's see. I know that y double prime of t, which is going to equal v prime of t, is equal to a of t. So I'm looking for a of 3. I just got to relate it to the graph somehow at 3. Okay, so here's 3. I got my spot located on the graph. The y values are the positions, yeah? So I know at 3 the particle is at the origin on the number line. He's at 0. The slope is the velocity, so I know that at that moment he's moving down 6 inches per second, right? What's the acceleration on the graph? 0. Why? Very good. That's what it is. It's the rate of change of the velocity because at 3 on the open interval containing 3 to the left and right, it's part of a line, and a line has a constant velocity, and a constant velocity by definition doesn't change. Excellent. Excellent. So the particle's velocity at 3 is 0 feet per second squared. Good thing it wasn't curved, right? We'd have a real difficult time without an equation determining that, because you have to figure out how fast the graph is changing at that. No. So if they're going to ask you something like that, it's going to be an answer they expect you to calculate. Excellent. So it was really the same thing we did up here, but up here we had an equation of the position, and it was moving horizontally. Down here we had a graph of the position moving vertically. So you can't just talk about, y prime and y double prime when you don't have the equations. You have to kind of always relate it back to what you're looking at on the graph. If it asks you to justify, it means we're in court and, someone's life is on the line and you need to really convince the jury. So you need to lay it out there for them in great detail. All right? All right, questions on that one? Did that sheet make it all the way around? Yeah? Who wanted to run it to Miss Norris for me? Do you mind going now, or do you want to stay for the next example? We got time. Yeah, let's wait. Just before the end of class. We'll run it down. Thank you. Okay, let's move to example 8. We have another graph. We can see that. They're easy to spot. Graph. The graph above shows the velocity. I was thinking of a bad joke. I didn't want to say it. No, I was just thinking a graph is easy to spot, and then I was thinking in my mind, you know what else is easy to spot? A giraffe. A graph is easy to spot, and so is a graph. A giraffe. Because, like something sticking up above that fence, what is it? A giraffe. Easy to spot. That's how my mind works, unfortunately. Example 8. The graph above shows the velocity v of t of a particle in feet per second. Is this a graph of position? No, it's a graph of velocity. So we're going to be looking at it a little bit differently than we did previously. So that's the first thing that you need to do whenever you're given an equation, whenever you're given a graph, or whenever you're given a table of values. What is that the equation, graph, table of values of? Is it position? Is it velocity? Is it a value equation, or is it a rate equation? Okay, because you're going to use it differently depending on what it is. We have units, feet per second, and we're back to moving along a horizontal line, and we have a closed interval from 0 to 6 seconds. So we have units as well, feet per second. Now we have feet, so I'm okay, not inches, feet and seconds. On what open intervals from 0 to 6 is the particle at rest? Well, on the previous problem, the particle was at rest when there was a horizontal line. But is that what we're looking at now? No. Okay, it says to justify. Let's go ahead and justify first. This is you thinking through. A particle is going to be at rest when it's lying in bed. And if it's lying in bed, assuming that it's not a movable bed, the bed should be stationary and the person should not be moving. So the velocity should be what? 0. So we're looking to see where the velocity is 0. Now, can I just say v of t equals 0? Did they give me v of t? They sure did. Now, where is v of t? The y values of this graph are v of t. It's equal to 0 at 1 and 4-ish? You have to go to 3 decimals, so can you put 4.ish? That's 3 decimal accuracy, 4-ish? Okay. We better find it. You think it's 4.5? 4.25. We shall see. You know what we got to do? We got to find it. How can we find it? It's made up of a line segment. We got 2 points, right? We got the point 3, -6, and we have the point 5, 4. Can we write the equation of that line? Yeah, we're going to do a little bit of showing off here on the side, a little bit of algebraic showing off. The slope of that line then is going to be 4 minus -6 all over 5 minus 3, which is going to be 10/2 or 5. So the equation of the line then in Taylor form is y equals, I'll use the 0.54. Either point will work, right? It's going to be the y value plus the slope 5 times x minus the x value, which is also 5. Now I'm just trying to see where that line crosses the x-axis, right? So I should set it equal to what? 0. So if I set it equal to 0 then, I get 5 times x minus 5 equals -4. X minus 5 then equals -4/5. And if I add 5 to both sides, I get x equals 5 minus 4/5, which is 25 minus 4 is 21/5. So you can leave it as 21/5, but that's the same as 4 and 1/5. And 1/5 is what as a decimal? 0.2. So either one of those, 21/5 or 4. You were close, James, so you would have gotten 0 points on that. Yeah. All right, so now we've shown the work for that. Now we can answer the question. V of t equals 0, we can just say for t equaling 1 second and t equaling 4.2 seconds. Now, I guess if we didn't have tunnel vision here with the notability, maybe the work for that is done down here possibly, right? On the actual free response, just like y'all have been doing on y'all's tests, you'll have a little rectangular space in which to work for each section. So you would do that work in that section. If it was done up by the graph, it would still be there and you would still get credit for it. So don't worry about that. Okay, was that enough justification? We answered it, right? What's the justification? V of t equals 0. Yeah, and this right here. In other words, they want to know why do you know that 1 and 4.2 seconds are the time where it's at rest, because that's where V of t equals 0. Part B, on what open intervals from 0 to 6 is the particle moving to the right? The particle is moving to the right when V of t is what? Greater than 0. That's when our y values are above the x-axis, yeah? So that's going to be from 0 to 1. And that funky x value, or t value, which now we know is what? 4.2 to 6. Okay. Now notice it said on the open interval from 0 to 6. So notice this is kind of interesting. At 6, we have a positive velocity, and at 0, we have a positive velocity. So you would want to include those if it was the closed interval, but you would not want to include 1 and 4.2 because that's where the velocity is 0. So if it didn't say on the open interval, you would say from 0 to 1 union 4.2 to 6 with the bracket, because technically at 0 and at 6 we do have positive velocity values. But it circumvented that whole thing by asking for the open intervals. So we don't have to worry about whether to include the endpoints or not. We'll just say for t epsilon, and then I'll change those to open, open. And what units do we have at the end of there? Seconds? Now again, the justification is right above there. V of t is greater than 0. You're basically saying, I'm looking to see where my graph that you gave me, that you called V, I want to know where it's positive. And there's the open intervals where it happens. Seconds. All right, on what open intervals is the particle moving at its greatest speed? When is the particle moving at its greatest speed? Now, Are we staring at the speeds? No. How is speed related to velocity? It's the absolute value. So speed is equal to the absolute value of velocity. Can we generate the speed graph? Heck yeah, we know how to do this transformation. To get the graph of the speed function, all you have to do is remember the absolute value of a function, leave all positive values alone, all positive y values alone. And what happens to the negative y values? They reflect up. So instead of 2 negative 4, you got 2 positive 4. And instead of 3 negative 6, you got 3 positive 6. So then it would look like this. And then it would come back down. And so the brown graph is the speed function. Now, do you need to graph that to answer the question? No. So having done that, let's just look at the speed graph since we have it. At what time or on what intervals is the speed the greatest? So where is that graph the tallest? At t equals 3, right? And at that time, the speed is 6. So there's no real, I guess if you want to graph it, you can. But if you recognize that all you're doing is you're looking to see where the velocity graph is farthest away on either side from the t-axis, you can get the same answer very quickly, right? Let's see, this on the positive side, it reaches 4, but on the negative side, it reaches negative 6. Well, that just means it's going 6 feet per second in the negative direction versus 4 feet per second in the positive direction. 6 feet per second is still a greater speed, yeah? So again, where is the graph farthest away from the t-axis? So we'll just say at t equals 3 seconds. And if it asks for the speed, you could say at this time. I don't think it did. Or did it ask for it? Yeah, at this time, the speed is, what do we say? Yeah, what was the magnitude of it? It was 6 feet per second. It just happened to be moving in the negative direction. Okay. Now it says, where's the greatest velocity? Is it the same thing? No. The greatest velocity is going to be where is it the most positive? Well, it would be at t equals 0 and on the interval from 5 to 6, right? So it starts off with that. So velocity is greatest when the graph is the most positive. The velocity is greatest at t equals 0 seconds to start with, and on the interval from, what do we say, 5 to 6 seconds. Now, let's stop right there because I just caught myself in an error. I was being very thorough. I would actually lose a point there, maybe, depending on how they would feel that year when they set up the scoring guidelines. This is good. I didn't include 6 right there because I kind of remember from the previous problem that I wasn't going to include the endpoint. But I included 0 for some weird reason. Was I supposed to? It says on the open interval from 0 to 6, where's the speed the greatest? 0 is not on the open interval, is it? 0 is at the left endpoint. So if I catch that, I'm going to come back and just get rid of that. So speed is the greatest at, or on now, I guess I should say, on that interval. So whenever you are given an interval, whether it's at the top of the question in the stem or it's in the individual part of the question, make sure you take special note of that because it's for a reason that they're telling you. All right, let's keep going. On what open intervals is the particle speed increasing? All right, this is fun. The speed is increasing.
Teachers and students, please pardon this interruption. Teachers, just a reminder, please send your signed rosters and any unclaimed report
Schroeder, you want to go now?
Norris's office by the end of this class period.
Let's do one of these. And we're
Channel 4 for the morning announcements. You can view them online at ehstv.com.
all right. When we're talking about speed increasing, we need to look at 2 things, right? We need to look at acceleration. There's a report card left in there, so thank you. Speed is increasing when the velocity and the acceleration are working together, yes? When they're both positive or when they're both negative. The y values of this graph are the velocities. The what's of this graph are the accelerations. Slopes. So speed is going to be increasing when the y values are positive and when the slopes are positive. Let's highlight those. Here's the positive y values first. And now which of those have positive slopes? Well, just from there to there, right? Also, we can have negative. So where is the y values? Where are they negative? Let's use purple. Well, they're negative here. And of those, where are the slopes negative? Well, the slopes are negative here and here. So it's only from 1 to 2 and 2 to 3. So on those intervals, so on the open interval from 1 to 2, union 2 to 3, and then from, of course, 4.2 to 5 seconds, the speed is increasing. So we'll say on that interval, speed is increasing. Because the y values and the slopes are the same sign. Okay? Now there's a quick way to determine that easily from the graph. I wouldn't use this as a justification, but anytime your graph is moving away from the t-axis, your speed should be increasing, right? Because your velocities are moving away from 0, and it doesn't matter the direction, right? That's a real quick way to spot it. Now notice I stepped over 2. Why did I step over 2 instead of just saying from 1 to 3? Yeah, the velocity or the speed is changing at 2. How is it changing? Is it changing in a way where that it's defined? Well, remember that the velocity and the acceleration have to be the same sign. So I know that from 1 to 2, the velocity is negative because the y values are negative and the slope's negative. I also know from 2 to 3 that the y values are negative and the slopes are negative. At 2, the y value is negative, but the slope is undefined because you have a little sharp turn. And if the acceleration then is that slope and the acceleration is undefined, you can't include it. You have to step over it. Okay, so that's why I did that. Now, you would have to say, if it asks how to justify, you would say basically, let's just look at this one interval. Speed is increasing on the interval from 1 to 2 seconds since, here's how you could say it, since v of t is less than 0 and decreasing. If you want to say it like that, that captures it, right? And you don't even have to get acceleration involved. Or you could say, since on this interval v of t is less than 0 and the slopes of v of t are negative. That's another way to do it without actually getting acceleration involved. You don't want to just throw out the word acceleration or v prime of t because you need to, again, relate it to the graph. So v of t is less than 0 and decreasing. That's beautiful. Or v of t is less than 0 and the slopes of v of t are negative. All right, so on what intervals is the speed going to be decreasing? Well, you can spot it very quickly. Speed is going to be decreasing when the graph of velocity is approaching the t-axis, right? Because that's where your velocities are approaching 0, which is when the speed is approaching 0. So then we'd say the speed is decreasing on the open interval from 0 to 1, union 3 to 4.2 seconds. And again, if you wanted to justify it, let's justify it for 0 to 1. Since on this interval, v of t is greater than 0 and decreasing. That means that the y values are positive. I got it, thanks. And the slopes are negative. Thank you, Schroeder. You're a great man.
Would you have to kind of, like on the first one, justify it twice for above?
Yeah, you would need to justify it twice. Very good.
So would you want to just...
Yeah, so let's go back to the blue one, right? We said the blue one right here from 1 to 2. You would actually need to do another justification from 2 to 3 that was identical to that. And then for this one, you would say since v of t is greater than 0 and what? Increasing, right?
So you just put like on 1, 2 because v of t is...
Yes.
And then you just repeat that.
Right, and then repeat it. You have to say how it changes. You can't just say because they're opposite signs, which would be great because then you can clump all of them together. So if they change for a different reason, positive to negative, negative to positive, you have to split them up and justify them separately. It's not a big deal, it's just a little bit of writing. What was your question, Clark?
I was just going to say, like, so you shouldn't probably write them all.
No, yeah, so even for the ones where the speed is decreasing, I would have to have 1 for that, right? V of t is positive and decreasing from 0 to 1, and v of t is negative and increasing from 3 to 4.2. Okay?
So you couldn't actually group those together where it's like on 1 to 2, union 2 to 3.
No, if you're answering the question, you could say speed is increasing. You could group all of them together, but then you have to say since and then break the justifications up. So you might just want to say on the individual ones. Now, if you had two different intervals that were like if these were connected, smoothly, well, then I guess you wouldn't need to split it up to begin with. But if there was another interval over here that it was going down like this, then you could group that justification and this justification together. It's a little bit of a burden, but that's part of what we're learning.
So you could, like, on the interval 1 to 2, union.
Yeah, if it was going down here and down there, then you could say on the interval from 0 to 1 and from 5 to 6. The speed is decreasing, since V of t is greater than 0 and decreasing. But they have to be doing it for the same reason. Okay?
So why wouldn't, I know the slopes are different, but 1 to 2 and 2 to 3, couldn't you group those together in this one?
For the justification?
Yeah. So
As long as you split up the interval, you could say from 1 to 2 and 2 to 3 cents on these intervals, yes, V of t is less than 0 and decreasing. Yeah, I'm sorry. You can group the justifications for those two together, but you still have to split up the answer. Great question. Yeah, you'll practice that in the worksheet. Let's see if we can keep going here in 5 minutes. What is the particle's acceleration at 4.8? Well, 4.8 is going to be right where? Right before 5. And the acceleration is the what of this graph? The slope. Did we already find the slope of that line? Yeah, so what was the slope? We're going from -6, so we're going up. Yeah, we're going up to, we have to go to another point on the line, which would be to 4. So from -6 to 4 would be up 10. And over from 3 to 5 would be what? 2. So up 10 over 2 is a slope of 5. Yeah, good. So it says show the work that leads to your answer. Guess what we'd have to show? We'd say V prime of 4.8 equals A of 4.8. And then you would just show your difference quotient, which would be, let's get the y values here. 4 minus -6 over 5 minus 3. 4 minus -6 over 5 minus 3. And then you can get 5, and it would be feet per second squared. So again, your difference quotient is important. 4 minus -6 over 5 minus 3. If it says show the work that leads to your answer, make sure you show that. On what open intervals is the acceleration the greatest? So it's kind of what we did above. The acceleration is going to be the greatest when the what of this graph is the greatest. Slope. Now, there is no speed equivalent to acceleration. There is no absolute value of acceleration that I know of. So we're not just looking for where the graph is the steepest. We're looking for the most positive slope or the least negative if they're all negative. So I'm thinking that it's going to be right there. That's the only slope that I have that's positive, so it defeats the negatives. So that would be from 3 to 5, yeah? So the acceleration is greatest on the interval from 3 to 5 seconds. G is for genius. What's the particle's displacement during the first 2 seconds? The displacement during the first 2 seconds. How can we figure that out? Well, that's not too much of a genius question, right? It starts at 4, and then we know that it travels in the first second, it travels down how many units? It goes down 4 units. And then in the next 2 seconds, it travels down 4. Am I using this graph right? Is this a position graph? No, it's not. Okay, so I can't just do that. If this were a position graph, it'd be that easy. Just figure out the change in the y values. How can we figure that out? It's the area. Good. Because, and this is getting into the second semester, if velocity is feet per second, and you want to get seconds, or feet, as your answer, which is the units of displacement, you're going to have to multiply by seconds to get them to divide out. If you divide, you get feet per second squared. Well, the derivative is a division process, right? It's the slope. Whenever you have to multiply, that's area, and that's going to end up being the integral. So if you can find the area of that, that's positive. If you can find the area of that, That should be negative, right, because it changes direction at 1. What do you know about the area of those two triangles? They're equal. So from 0 to 1, let's see what the area is. It's 1/2 the base times the height, so half the height is 2. So it travels 2 feet going up, but then it travels the same 2 feet going down. So what was its displacement? 0. The distance traveled was 4, but the displacement equals 0. Yes, the displacement is going to end up being the area under the graph of the velocity function. And that's the whole second semester, or most of it. Okay, we're done right there with example 8. We should be able to finish tomorrow pretty easily, so make sure you're working on the worksheet.